Let's understand the reasons that make conventional lenses less than optically perfect. Lens performance becomes lower as we look away from the optical center. This is a result of the oblique aberration that appears when light is refracted obliquely, which happens whenever we look in lateral gaze directions. Those lateral rays do not focus on the retina. Oblique aberration reduces the quality of vision outside the center of the lens. For high prescriptions and wrap frames, the effect is even stronger. This beam comes from the outer environment, refracts on the front and then back surface of the lens. The back surface is modified using this refraction so that the beam changes its focus to the center of the retina, the fovea. This procedure is repeated for every direction of sight until the entire back surface of the lens is adjusted, and all simulated beams focus in the fovea. The result is a fully optimized lens, improved not only in the center, but optimized all over the surface. A lens with accurate power in all gaze directions. A high-definition single-vision lens providing clarity from center to edge, resulting in the best possible lens for the wearer. For progressive lenses, oblique aberration correction is even more important. Stable, usable areas for far and near vision are located away from the optical center, so lens optimization is more significant. Far vision, intermediate vision, and reading vision as well. In the upper part of the lens, designed for far vision, the passage of rays coming from distant objects is simulated. In addition, the calculation takes into account the vertical movement of the eye and simulates the rays representing the intermediate vision. Finally, there is a simulation of rays from objects closest to the eye, the reading zone. The ray tracing method is extended to include the space object. This mathematical model simulates thousands of rays coming from different zones through the front and back surface of the lens, which is optimized during the beam refraction. It is essential to optimize the progressive design of modern rimless or sports frames with a large curvature. Here, the lens is often skewed and turned towards the eye, which significantly changes the viewing angle of individual zones. Based on the digital ray path method, these zones are maximized and optimized for both the biometrics of the wearer and the shape of the frames. The result is comfortable near vision as well as distance vision.